Hello, this is the last unit on derivatives, and now we know how to take derivatives of functions. We know how to look at the graph of a function and interpret the sign of the derivative or second derivative. So in the last unit, we're going to look at some applications. Um, Optimization is a broad class of problems. What does optimization mean in English? It's making something the best it can be. So these are all going to be word problems, and there's actually no new mathematics here. It's just interpreting what you know. Think about optimization problems sort of like related rates meet extreme value theorem. So similar in field to related rate problems, but instead of just looking for relative rates of change, we're looking for either a maximum or a minimum of some kind of objective function. And you'll see what I mean with examples. Uh, we're going to use the extreme value theorem and find the maximum or minimum occurring at either a critical point or an endpoint of the domain. Okay, and again, you've already seen all the skills you need, so it's really going to be just practice makes perfect. So let's review a couple general problem-solving tips for mathematic word problems. The first things first, you have to read the problem carefully. A lot of students think they can guess what the problem is asking about, or they're in a rush. And if you start writing down equations and doing computations, there's a high chance you're just going to be wasting your time and maybe not even answering the question that's being asked. And sometimes for a tricky question, interpreting what the question means correctly is half the battle. To help us out, we always want to draw a diagram if one is not given, if it's appropriate. And of course, we start word problems by defining variables, again, if it's not already given in the question. Then we'll write equations based on the problem statement or on the diagram or on general knowledge. And we want to restate the goal of the word problem in terms of defining a function that we have to find a maximum or a minimum value of. We want to convert word problems into abstract math problems. And once you've got to that stage, all we have to do is a little calculus, a little algebra, and we're done. And of course, when you are done, we can double check that the answer makes sense in the context of the question. So here's one example problem. We'll call this the efficient cup problem. The question is, find the dimension, height, and radius of a cylinder with no top, we'll call it a cup, and it has a fixed surface area of 16 pi square centimeter, and we want it to have the maximum possible volume. Okay, so we'll start by writing down some equations to relate the variables. And I'm not going to explicitly define the variables. I think that because they're kind of typical variables, we can understand the meaning from the equation. So volume equals pi r squared h. That's the equation for volume of a cylinder. And the surface area of a cylinder is the area of the base, that's pi r squared, plus the area of the cylindrical wall. If you unroll that wall, it's a rectangle with height h and base circumference of the circle. So 2 pi r h is the total surface area. And from the question, the surface area is fixed at 16 pi. Okay, restate the goal. We want to maximize V, and we'll state the domain R. Radius should be between 0 and 4. And we know that the radius can't be larger than 4 because if it is, pi r squared is bigger than 16 pi. That's the total surface area we're allowed. And of course, the radius has to be positive. Doesn't make sense to have a negative radius. As a subtle point, I don't have equality in radius cannot be equal to 0 because then we don't really have a cup at all. Okay, so in a related rates problem, we might take derivatives before doing any substitutions. In this case, I'm going to substitute. I'm going to solve the surface area equation for h. So h is going to be 16 minus r squared over 2r, and I'll plug that in to my volume equation. So now I've got volume as a function of one variable, r. So I want to maximize this function on the domain 0 to 4. Okay, we've gotten rid of the words. It's just letters now. So I'll take a derivative, dB dr looks like this, and solve for 0 to find the critical points. And r would be plus or minus 4 over square root 3. And of course, we ignore the negative solution. At the endpoint, when r equals 4, we have 0 volume, so our only critical point must be the maximum. We could do a second derivative test to double check, but in the context of the question, this is clear. And so we just plug that in to solve for h to find the dimensions of the cup. And in this case, both the radius and the height are equal, and that will give us the maximum volume.